Section 2 is going to deal with wave-like properties of electrons. Abstract, so we're going to be doing some abstract thinking. I have pictures and diagrams that I can show you, but I can't say, here's an electron and watch it move. So there's a little bit of abstract thinking as we're looking at electrons move from one place to another. How does that affect their spectrum? How does it affect their energy? And where do these electrons go? So that's kind of the big idea of what we're going to talk about today. Essential questions, these are at the end. Bohr's model. Bohr's model is going to be very big in understanding because we'll use that to look at our electrons and where they're at. So you'll want to understand how to draw, how to use a Bohr's model. De Broglie's wave-particle duality, we'll talk about it. I'll kind of show you it. There is a formula. We won't use that formula. I just want to show you what it's used for. Heisenberg uncertainty principle, you'll want to know what that is. And then this last bullet is what we'll spend a lot of time on the next 2 days. What are relationships between energy levels, sublevels, and atomic orbitals? What's the difference? What does it mean? Where do the electrons go? And here are your vocab words. So, to start it out, a little bit of background. Einstein's theory of light accounted for several unexplainable phenomena, but not the spectrum part. How come each element had its own spectrum? He did not know why that was. Niels Bohr, obviously he's important because we're going to use his model. He worked with Rutherford, he worked in his laboratory, proposed a quantum model, and they worked with hydrogen. So hydrogen was the first atom that was worked with, and worked on answering about the spectrum. Both correctly predicted that these frequency lines would show up in the atomic spectrum. And here's a vocab word. The lowest allowable energy of an atom is ground state. In simplified terms, this is where the atom wants to be. This is the recliner. So this is where an atom wants to be. It's the lowest energy, it is ground state. When electricity or heat or something is added to the atom, then the electron is going to move to an excited state. So it always starts at ground zero, starts in the ground level, and then when it's excited, it's going to move to a different level is where it will go. So if I look at this, Niels Bohr suggested that an electron moves in orbits, very much like planets orbit around the sun. That's pretty much what his model suggested. So if we are looking at electrons as particles, his model is fantastic. I can say, okay, this electron's in the first energy level, this electron is in the second energy level. I have added electricity, so it's moved from the first to the second. I added electricity, so it went to the excited state, and eventually it will drop back down and go back to its ground state. Each orbit was given a number called a quantum number. And N stands for quantum number. If I have one quantum number, I'm going to have one energy level. So these two columns to me are the most important. I do not expect you to remember a radius. I will not quiz you on anything here. Energy, this is just showing the amount of energy. We won't calculate or use that. It is these two right here. If I have a quantum number of 2, I'm going to have 2 energy levels. 3 has 3, 4 has 4, etc., etc. So when we start looking at orbits, so if I have hydrogen, it has one electron and it is in the first orbit. So it has a quantum number of 1 and it only has one energy level. That's all that it has. If I look at sodium, and this is on your periodic table that I printed off for you guys. If I look, it has 2, 8 electrons, and 1 electron. It has 3 orbits, so it has a quantum number of 3, and it has 3 energy levels for those electrons to fit in. And we will talk a lot more about that. Whenever energy is added, an electron can move. So if I add energy to my sodium, these 2 electrons might move up here and join the group 8, while some of these might move up here. So whenever energy is added, electrons move to a different orbit. In hydrogen, there's only 1 electron, so it's going to move up to the second orbit because there is only 1 electron. So, if I'm looking at this, there's different parts in your electromagnetic spectrum. There's the visible series, which is visible light, also called the Balmer theories. What I want you to know is that all Balmer series go down to level 2. So when they go to their ground state, it's energy level 2. If I look at infrared, it's level 3. And if I look at my UV series, they are all going to be energy level 1. So no matter where, notice here that this electron is moving a lot further than this one is. So that's going to affect how much energy is gained or lost. If it's traveling a larger distance, it's going to affect the amount of energy. Here, I'm going to come back to these. I'll come back to those. So limits. Bohr's model is still fantastic. We still use it. However, there were limits to his model. It did explain the spectral lines, but it didn't explain any other elements. Basically, this is saying the only thing that Bohr looked at was hydrogen. He didn't look at any other elements. The behavior of electrons was still not fully understood, but it did indicate that they don't move around the nucleus in orbits. So after further research, he doesn't think that they stay in those orbits. They can move from one place to another. So, moving on, after Bohr's model. Then we have the quantum model. So de Broglie hypothesized that particles, including electrons, could have wave-like behaviors. So they don't only act like particles, they act like waves. That question was on your last test, very possibly could be on the next test. Same thing, I can look at it as a particle, I can look at it as a wave. So here, all this shows is that electrons are going to orbit the nucleus in wavelengths. So here I have a whole wavelength, and it's just showing how electrons can orbit. It's not a nice, neat little circle. It's not like a planet in a path. If I'm actually looking at electrons in motion, they're not going to move in one tiny little circle. That's basically what this slide is telling you. Here's his equation. And like I said, we're going to go over this. We're not going to use it. You're not going to have to plug anything into this formula. But de Broglie came up with an equation basically that says all particles also have wave-like characteristics. And I can calculate that. I can use my wavelength and Planck's constant. I'll look at the mass, I'll look at velocity. I can plug it in, and I can find a wavelength for anything that has mass and is moving. So basically, de Broglie's equation shows that moving particles have wave-like properties. And he used math to help reinforce that. When he did that, they started to find that I can't know speed and position of something at the same time. So if I am watching you run track and you're running the 100, I can't say, oh, she's at 10 meters, because the minute I say she's at 10 meters, she's what? She's already past that. She's at a different spot. So Heisenberg uncertainty principle states it is impossible to know speed and position at the same time. I either have to study electrons as a wave, or I have to study them as a particle, but I can't do it both at the same time. And that's still true today. I can't take a measurement of one thing without messing up the other part of it. So the only quantity that he could come up with is the probability for an electron to occupy a certain spot. So here's a photon, a little packet of light. It hits an electron. When this hits the electron, it's going to be deflected. So my photon goes this way, and my electron goes that way after they have collided. And then I can see that I can study this as a wave. The wavelength increases. Here my electron is going off the other direction. So I can look at a wave, and I can look at a particle, but I can't look at an electron as a particle and a wave at the same time. I can only do one or the other. And you should know that this diagram deals with Heisenberg. You might see this diagram and should know that that is part of Heisenberg's work. Schrödinger then treated electrons like waves and called it the quantum model of the atom. His equation applied equally well to all elements, not just hydrogen. So we have someone looking at more things. And what he found is that, or he predicted that there's a region around the nucleus called the atomic orbital. And that orbital is where you're most likely to find the electrons. So this would be like a density map showing where you're most likely to find electrons. And you're going to find more of them closer to the nucleus and fewer of them further away from the nucleus. And I'm going to stop and come back to this in a little bit, because this will be big stuff.